Cool, thanks. Hi, everyone. So, always great to start a talk with a whole load of disclaimers. When I was writing this, I found out that it's actually quite hard to teach neural nets from scratch in 30 minutes. But it's OK. The aim of this talk is to give you an intuition to how they work, not to make you understand all the maths. So we're not going to get bogged down with loads of maths. We might have to go quite fast, so don't worry if you don't follow everything. I'm just hoping to kind of introduce you to certain concepts, and you can always go away and read more about them if you want to. We're going to make some simplifications, and we'll probably have to miss out a lot, but the stuff that you're hearing will still be accurate. And basically, I'm giving the talk that I wish I'd seen when I started learning this stuff. I started learning it about a year ago, and it took me a really long time to just even understand what all the words mean and be able to read through a paper and actually have an idea about what was going on. And I think a talk like this would have really helped. So just a bit about my background. I'm a technologist at BBC R&D, which is the part of BBC which is responsible for looking into new kinds of technology that could be useful for broadcasting and media. My background is in computer science, physics, and philosophy, and I'm currently also studying for an NGD in machine learning for visual computing, and that's kind of what got me interested in this topic. And because I started to get interested in neural networks, artificial intelligence, that kind of thing, I co-founded a community group called Manchester Futurists, where we are trying to look at the impacts of these kinds of technology on the future and how we can make sure we end up in a utopia and not a dystopia. So we're going to try and cover a few things. First, we'll look at how neural nets and conventional computing compare. We'll look at what is a neuron. We'll then see how they combine to make a neural network. We'll then quickly look at how to train a network, and then we'll move on to looking at something called convolutional neural networks, which are just a kind of special type of neural network, and then some of the fun applications that you can use them for. So a bit about the history. This is not a new idea. Neural networks were actually started in the 1940s, and at that point they were called cybernetics, which I actually think is a much cooler name, and I think we should bring that back. But they were abandoned to some perceived logic limitations. So for example, they're not able, a single layer perceptron is not able to model the XOR function. Then in the 1980s, there was a bit of a resurgence, and at that point it was called connectionism. But it was abandoned due to a lack of capable hardware, and also there weren't kind of big enough data sets around to use to train the networks. Then in 2006, there was a bit of a resurgence again, and we're now calling it deep learning. And at this point, we've got really good hardware, we've got much better GPUs, that kind of thing, and we have the internet, which provides a huge source of data. So maybe now the time is right for deep learning, and maybe we can expect it to stick around. OK, so let's take a look at conventional computing first. So if I want to have a task which is to recognize a cat, if I was trying to program a computer to do this at the moment, I would basically have to have a whole load of if statements telling it how to recognize a cat. So if it's furry, and it has a tail, and it has 4 legs, and it has pointy ears, etc., which, as you can imagine, you're going to have a whole load of stuff. And it's also not that useful because it doesn't take account for kind of edge cases like a 3-legged cat or a cat that doesn't have a tail. And also, the examples I've given here, you could also say that they would apply to a dog or a fox or something, so it's not really that helpful. But basically, you're programming explicitly what features that the computer should be looking for. With a neural network, on the other hand, instead of programming it explicitly, you just say, here are a load of cats, here are a load of not cats, you work out the difference. And that's a lot more like we as humans learn to do things when we're little, and that's how we kind of learn to recognize what isn't a cat, is by examples. And so the machine is actually working out what features to look for. You don't have to explicitly tell it. So this is just a little visualization of the kind of thing I mean. So on the left-hand side, we've got a nice straight line that's trying to divide up the red and the green dots, where the reds are cats and the green dots are dogs. And this does a relatively good job, but you can see that it's missing quite a few cases, which the dots are on the wrong side of the line. But it's a nice, easy thing to model with a computer. You can just use a nice kind of y equals mx plus c straight line, which we all did in GCSE maths. But on the right-hand side, you can see a much more complicated representation of this. And in this case, it's actually catching all the dots in the right kind of category. But if you wanted to try and write a nice equation for a straight line to do that, that would be pretty difficult. But that's exactly what a neural net is able to do. It kind of learns this complex multidimensional model, which makes it much more robust. So they're called neural networks because they're inspired by biology. And as I said, the machine is learning a complex multidimensional model. And that's why it can tell the difference between cats and dogs, or recognize those strange edge cases like three-legged cats. And my rule of thumb for thinking about this is that neural nets are good at things that humans are good at, like pattern matching, and they're bad at things that computers are good at, like maths and logic. So let's look at a trivial example to try and get an idea for how they work. If I was trying to decide whether to go to a festival or not, I would think of a whole load of different factors. So will the weather be nice? What's the music like? Do I have anyone to go with? Can I afford it? Do I need to write my thesis? And will I like the food? And I'll think about those, and I'll be weighing up the pros and cons and trying to figure out, are there enough reasons to make me go to the festival? And we can kind of represent this in a diagram. So taking the first 4 examples I gave, so weather, music, company, and money, I would then think about how important those things are to me. So multiply them by their importance, add them all up, and if it's over a certain threshold, yes, I'll go to the festival, and if not, I won't go to the festival. So to put some numbers on it, let's say the weather's looking pretty good. It's a kind of a 3 out of 4. The music, it's not my favorite, but maybe it's all right, so I'll give it a 2 out of 4. Company, my best friend has said she'll go with me, so I'm really happy about that, so 4 out of 4 for company. And then money, I can't really afford it, but I have got a bit, so maybe I'm OK. So I'll give it a 2 out of 4 as well. Then we multiply it by the importance. So just take the weather for an example. Let's say it's really important for me that the weather is nice. I don't want to go to the festival if there isn't nice weather, and I really do want to go if the weather is nice. So I'll give it a 4 out of 4, and so on for all the other factors. You then multiply them all up. You add them together. You find out what they equal. You check whether or not it's above my arbitrary threshold, which I've chosen here as 25. And if it is, then yes, I'll go to the festival. So another thing from GCSE maths, hopefully you'll remember that if you've got something on one side of an equation, you can just move it over to the other side of the equation. And that's what happens in a neuron. So we have all our importance values, and then we have this factor that we have moved over from the other side, and that's what's called a bias. And it took me ages when I was reading about this to figure out where the bias came from when I was reading about neural networks, and that's what it is. So this is the kind of general representation of it. You have a load of inputs. You multiply them by their weights, which is the importance. You include the bias. You add them all up. You see if they, you put them through this activation function, which was our threshold, and then that gives you your output. So that's what's in one neuron. To make a neural network, you simply chain up loads and loads of these neurons together. So you have an input layer, and then the outputs of those neurons feed into the next layer, and then the outputs of those neurons go into the next layer, and this can carry on as many times as you like until you get your output layer. And in order to make a deep neural network, you simply need more than one hidden layer. So it's quite straightforward, really. You just need these 4 layers. OK, so far we've only seen a binary output. So we were looking at the festival, and we were giving a yes or no whether we should go to the festival. But what if you want an output that isn't binary? This is where the activation functions come in. So far we've used this step function. So it's just above or below a certain amount. But historically, a really popular activation function was called the sigmoid function, and that's this kind of S-shape graph here. And all that means is that at very, very low values, you're going to get a 0, and at very, very high values, you're going to get a 1, and then in between, you'll get something a bit more gradiented. These days, the most popular function is called ReLU, which stands for Rectified Linear Unit, and all that means is that if your input to the function is 0, your output will be 0, and if your input to the function is greater than 0, your output equals the input. So you have this shape. And those graphs go in this activation function bit here. So it's just taking the result of the multiplication and addition, and then putting them into the graph and reading off the value, and then that's your output. So isn't it all just simple arithmetic then? It should be fairly straightforward. Unfortunately not. The difficult bit is actually figuring out what all the weights and biases should be. And so in the examples that I've given, I've just manually chosen how important things are to me. But when you're trying to train a computer to do something, it doesn't know what the right values for those weights and biases should be. And we have to figure those out by training the network. So the short version of training the network is you randomly initialize all your network weights and biases to just random numbers. You then get a ton of labeled training data. And for every piece of training data, you check whether the network gets the right answer or not. So if I put in a picture of a cat, I put it through the network, and I see whether the network says, yes, you're a cat, or no, you're not a cat. And if it's not a cat, if it gets it wrong, then I ask, how wrong was it? And then I nudge the weights a little bit to increase the probability of the network getting the answer right the next time you put training data in. And then you repeat that loads and loads and loads of times. So just to visualize that, I put my picture of a cat into the network, and for now, just imagine that the input is the pixels of the image. So instead of having music, weather, all of those things, just imagine that the value for each pixel is those inputs. We put them in, they go through the network, and we have the output layer saying that this picture is 62% chance that it's a dog and a 38% chance that it's a cat. And that's wrong, obviously, because we want it to say you're 100% a cat. So we know that it was wrong, we check how wrong it was, and then we go backwards through the network, and we just nudge the weights a little bit. OK, let's go into that a little bit further. So this gets a bit tricky, and so don't worry if you don't quite follow it. As I said, I just want to give you an intuition about it, so you can always go and read up more if you want to. So how do we know how wrong the network is? Well, we measure the difference between the network's output and the correct output. And we do that using something called the loss function. The loss function is also called the error function, the energy function, or the cost function. And that's another thing that no one tells you about when you start reading about this, but they are all the same thing, as I figured out a very long time later. And the best loss function will depend on the type of your data and the intended application. But you can think of a simple example as the mean squared error. So do you remember at school trying to fit a line of best fit to data points, and you basically look at the distance between the line and the data points, and you try and minimize the distance between those, the line and the data points? And that's exactly what a loss function is doing, just in many, many, many dimensions rather than just 2 dimensions. So they can get mathematically complicated, but just think of it as the difference between what the network should output and what the network does output. So our goal is to find the values for the weights and biases that minimize the loss function. So let's have a look at how that works. Imagine we could plot the loss function against all the weights in the network. So in this representation here, we've got 2 weights dimensions and we've got 1 loss dimension. But in a real neural network, you're going to have thousands of weights dimensions. But I can't think very well in thousands of dimensions, so let's just stick with 3D for now. So you can see the red parts of this landscape are where the loss function is highest, and our goal is to minimize the loss function and find the weights that make you have the lowest value for the loss function. So we want to go from the starting point, and we want to get right down to the lowest point we can, which is this blue bit here. Unfortunately, the network can't see this landscape. It can only see where it is, and it can only see its kind of little neighborhood. So it doesn't know where the lowest point is, and we've got to try and help it get there. And the way we do that is using something called gradient descent. And this is a bit like if you're standing at the top of a mountain and you know you've got to get to the bottom, but it's really, really foggy, so you can't see where you're going. So what you do is you put your foot out a little bit, and you feel around with your foot, and you try and find the bit that has the steepest slope, and then you take a little step in that direction. And you don't want to take too big a step because you might fall off a cliff, but you don't want to take too small a step because then it's going to take you absolutely ages to get down. So that's what gradient descent is doing. It's finding the direction of the steepest slope downwards, and then taking a small step in that direction by nudging the weights. So let's have a look at that. So we start with a very high loss function, and that means that the network is basically getting things completely wrong. So if we put in a picture of a cat, it's getting it sort of not quite sure, 50-50-ish, but it thinks it's a dog, and then the dog picture, it thinks it's a cat. So this is not good. We want to improve that. So we take a small step in a direction, and we lower the loss function, and that means that the network gets a little bit better. And we keep taking steps down the mountain, and as we do so, the network gets more and more accurate in its predictions, and it gets more and more confident, until we get to the very, very lowest point. And at this point, it's pretty much getting it 100% right that a cat is a cat and a dog is a dog. So mathematically, we calculate the slope using differentiation. And you start at the output layer and work backwards through the network. And that's what's called backpropagation. So if you read about it and you see the words backpropagation, that's what that's referring to. And we then nudge all the weights a little in the direction we calculated. And the amount we nudge it is determined by the learning rate. So the learning rate is the equivalent of the size of the step that you take. OK, I know that was a bit much, but it's OK if you didn't understand it all, because Tensorflow basically does it all for you. So Tensorflow is Google's open source Python machine learning library, and it comes with lots of inbuilt functions, which means that it takes care of most of the tricky math, so you don't have to worry too much about how it works. There's really good documentation, and there's loads of tutorials about it, so you can go and have a play fairly easily, but I definitely find it helps to have a kind of basic understanding of what's going on, even if you don't really understand all the maths behind it. OK, so now let's talk about convolutional neural networks. So these are a specific type of neural network. And instead of treating each input as an independent value, so if you think about the examples we've had with the festival example, and also I said about putting in an image and thinking of each pixel as an independent value, ConvNets don't do that. They take advantage of structure in input data. And images have a 2D structure. If you think about what an image is, if you take a random pixel from an image, there's a pretty good chance that the pixels around it are going to be somehow related. There's usually kind of patches of color in images. It's not completely random. And so ConvNets take advantage of that, and that makes them great for image processing and computer vision tasks. So just to recap, in case you're not familiar with this, images are just 2D arrays of numbers. So I've got a hand-drawn 3 here, and if I pixelate it to just illustrate what I'm talking about, and zoom in on a little part of that image, you can see that all the black pixels have a value of 0, and the bright white pixel has a value of 1. And then the pixel that's kind of grayish in between has a value of 0.8. And this is true for all images. Here it's just black and white, but you can have the same thing for colored images, but you just have 3 layers, red, green, and blue, and each one will have a value in this way. OK, so what is a convolution? Well, it's kind of like a fancy multiplication. And basically, we take what's called a kernel filter, which is just a small array of numbers, and we pass that over every pixel in the image. And as I said, images are just arrays of numbers. So you're just taking a kind of small patch of numbers, passing them over the image, which is a bigger patch of numbers. You multiply them all together, add them up, and then you put the value in a new array. And that's what convolution is. And we use this all the time without even knowing it. So in your phone, when you take a photo or use Photoshop, if you ever blur the image or sharpen an image, all it's doing is using a particular kernel filter, passing it over your image, and then you get your results. So for a blur filter, you essentially just take the average of the neighboring pixels, and that kind of makes sense. If you look at a single pixel, you look at the pixels around it, and then you just sort of take an average, and that kind of smudges it and blurs it. And then to do a sharpening effect or an edge detecting effect, you just kind of do the opposite. So you enhance the middle pixel. In these cases, you multiply it by a 5 or an 8. And then you kind of downweight the neighborhood pixels. So you're really enhancing the pixel you care about and downweighting the pixels around it. And that's what gives you these different effects. So let's go back to our representation of a neuron. We had a load of inputs. We multiplied them by a load of weights and a bias, and we added them all up. We put them through an activation function, and that gave us our output result. A convolutional neuron is very similar. We have a load of inputs. They just happen to be images or arrays of numbers this time. Instead of the multiplication operator, we now have a convolution operator. And instead of having each input have its own weight, we now have a shared kernel filter, and the numbers within the kernel filter are actually the weight values that we need to learn. We have our bias, we add it all up, we put them through an activation function, and we get our output result. And in this case, it will output an array rather than a single value. So if I just flip between the two, you can see that the structure is basically the same. OK, so that was the theory done. Now we'll look at some of the fun applications. So there's something called the ImageNet Challenge, and that's all about trying to use computers to recognize objects. And this is a kind of set of example results from the ImageNet Challenge. So you can see on the right-hand side there's a leopard, and this particular algorithm has got this right. It's got a high percentage chance that it's a leopard, but it's also got a little bit of a percentage chance that it could be a jaguar or a cheetah, which is fair enough. So until 2011, a good result in the ImageNet Challenge was 25% error. So that's still getting a quarter of things wrong, but that was considered a good result. But in 2012, ConvNets were introduced, and the error plummeted to just 15.3%, which is a huge step change. Before, it was tweaking it by 1 or 2%, and now it's dropping by almost 10%. So that's a massive reduction in the error. And then, in fact, in 2015, ConvNets were actually able to outperform humans for the first time. So they were able to get more objects right than a human could looking at this. So they were a real revolution in the kind of computer vision industry. So let's have a look inside a ConvNet. So remember I said we take our little mini array of numbers and we pass it over the bigger picture. This is a visualization of what's inside those mini array of numbers. As I said, images are just arrays of numbers, so we can actually visualize what that array of number looks like. And you can see that in the early layers, what it's finding is sort of general shapes. It's looking at lines and edges in different orientations. It's got kind of patches of color. And that's the sorts of things that it's learning to recognize in the early layers of the network. In the middle layers, it's starting to put things a bit more together and see a bit of structure. So you can see kind of some stuff that looks like circles and corners. It's kind of building up what the sort of component parts of objects. And then finally, in the later layers, you can see things that actually look a lot more like objects as we recognize them. So you can see kind of a tire and a sort of honeycomb thing. And I don't know if that's like a duck or a goose or something down at the bottom. But yeah, so it's learning to actually recognize objects. And they've actually found that this is a lot like how our human visual system works as well. So this was a really interesting finding from convolutional neural networks. And what they realized is that if a network is learning to recognize an object, it should be able to recognize that object whatever the style is of the picture. So if I hand draw a cartoon of a cat, or I give it a photo of a cat, it should still be able to recognize that a cat is a cat. And so what the network is doing is learning to kind of abstract away the style. So it has these layers in it that are really focused on picking up what the object is. And then it also has layers that are learning what the style is, and then they're just sort of ignoring it. They're just abstracting it away. But these people here, they found that they could actually make use of those style layers. And if they took the object recognition layers from one neural network, from one image, and applied them and took the style layers from another image, and then they could put them together, you could actually make these kind of weird works of art that are made from just everyday photographs, but they look like they've been created in the style of famous masterpieces. And I had a lot of fun using this app called Prisma, which actually uses this convolutional neural network algorithm. And you can take a photo of yourself, and then you can just pick whichever artist you like, and it will give you your face in lots of different representations. And this is actually the algorithm that it used. But they can be fooled. So here we have an example of a truck, which was correctly classified by the network. But then they found that if they added imperceptible distortion to the image, so it looks no different to the human eye, but actually it completely fools the computer, and for some reason it's decided that it is now an ostrich. And apparently this is 100% goldfish. I don't know. So you might have heard of Google's Deep Dream. And what they did was they took a trained convolutional neural network and they ran the process in reverse. So they said to the network, whatever you can see, enhance it. And instead of then going back and nudging the weights in the network, they actually nudged the image, the pixel values in the image. And then they repeated that over and over again. And then you get this kind of strange effect. So here's a before and after. And on the before, we've just got a nice landscape picture. But on the after, the computer has hallucinated these sort of buildings and cars and dogs and things like that. Another example is here. And another example is here. And And so you might be wondering, why are there so many dogs? And the answer to this is basically that the network that they were using had been trained on everyday objects, so everyday objects like buildings, cars, and dogs. And that meant that the network was kind of predisposed to seeing those sorts of things. It's a bit like how humans tend to see faces and everything. It's a kind of pareidolia. And this is what we call algorithmic bias. And it's very tempting to think of machines as being sort of objective and infallible, but in fact they are neither. And the network is seeing what it's been trained to see. It can only ever be as good as the data you give it. And that means that humans can transfer their own biases into these machines, and you can get networks that inadvertently learn proxies and correlations instead of true insights. And that can produce racist and sexist and otherwise irrational results. And there have been some examples about that in the news. One that I read about recently where they were trying to predict how likely it is for criminals, that whether the criminal would reoffend. And they basically found that white people, yeah, you're all fine. But if you're a black person, oh, you're probably going to reoffend. And that it's just a completely racist result, that it's learned from the sort of flawed data set that we give it and the sort of racist structures that we have at the moment. But there are things that you can do to help. So first of all, you need to try and understand your own unconscious bias. If we can be aware of our unconscious bias, it gives us a little bit more defense in terms of trying not to then transfer it. You can also use something called output testing, which tests whether the network has learned what you actually want it to learn and not just a convenient correlation. Another good tip is to diversify your training data and just remember that if you use training data of everyday objects, your network is going to be predisposed to that kind of thing. And of course, also it's worth remembering to diversify your engineering teams. If we can have lots of people from lots of different backgrounds coming at this problem, then we're much more likely to have a kind of a less narrow approach and hopefully reduce the biases. So there's a lot we haven't covered. But it's OK, because this guy he's like one of the main guys in neural networks at the moment, and he tweeted, "Everything I know about design of convnets is useless in real life. Super basic 4-layer convnets work best." And if you remember, we've learnt about what a single convolutional neural network neuron looks like, and we've learnt what a deep neural net looks like, and a 4-layer network, and how we can put them together. And as I said, you can just construct these nice and easily with Tensorflow. So you're sorted. Thank you very much.